Tonight, we are going to understand what the James Webb Space Telescope found in the early universe and why those findings have shaken cosmology in a way that nothing has in decades. There is a standard model of how the universe came to be. It has been tested by every major instrument ever built. It survived every challenge. It is the foundation on which the last 30 years of cosmological understanding. Webb was designed to confirm it at greater depth and clarity than had ever been possible before. That was the plan. And Webb did what it was designed to do. It looked deep into the early universe. It measured what was there. The results came back. And what was there was not what the model said should be there. Not by a small margin. Not by the scale of margin that calibration can fix. The galaxies that should not exist were massive. They were chemically rich. And there were hundreds of them. By the end of tonight, you will understand exactly what was found, why it cannot be explained by our current best model of the universe, and what it means that a species built an instrument precise enough to find the edges of its own understanding. If this type of science keeps you up at night in the best way, the subscribe button is right there. It costs nothing. It helps this channel continue making scripts like this one. Now let us begin. The James Webb Space Telescope was not built to find something wrong. That sentence matters. It reframes everything that follows. Webb was not a probe sent out to test a failing model. It was not a crisis instrument. It was the culmination of 25 years of engineering, a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, assembled at a cost of $10 billion and designed for one purpose: to see further back in time than any telescope ever built, and to see what was there with more precision than had ever been possible. To understand why that matters, you have to understand what looking into the distance in space means. Light travels at 186,000 miles per second. That speed is constant. It does not change based on what is emitting the light or where the observer is standing. What this means practically is that light takes time to cross distance. The light reaching your eyes from the far side of the room left that wall a few nanoseconds ago. The light reaching you from the sun left the sun 8 minutes ago. The light reaching us from the nearest star left it more than 4 years ago. And the light reaching us from the most distant galaxies, the objects at the fringes of what any telescope has ever detected, left those galaxies billions of years before the Earth existed. When we point a telescope at the distant universe, we are not seeing what that part of the universe looks like now. We are seeing what it looked like when the light began crossing space toward us. A galaxy 13 billion light years away is a galaxy as it appeared 13 billion years ago. We are not observing a distant location. We are observing a distant moment in time. Hubble, the telescope that came before Webb, the one that produced the deep field images that reshaped cosmology in the 1990s, operated primarily in visible and ultraviolet light. Hubble could see far. What it could not do as effectively was see through the cosmic dust that fills much of the universe, and it struggled to detect the most distant objects, the ones that existed in the first few 100 million years after the Big Bang. Webb operates in infrared. That is the key difference. Infrared light is light that sits below the red end of the visible spectrum. It is the type of light that carries heat, the type a thermal camera detects when it shows you a warm handprint on a cold surface. Infrared passes through dust that would stop visible light entirely, and it has a second property that makes it essential for looking back in cosmic time. When an object is moving away from us, its light gets stretched. The further away the object, the faster it is receding, because the expansion of the universe is carrying it away from us, and the more its light gets stretched toward the red and infrared end of the spectrum. An object 13 billion light-years away has had its light shifted so far toward infrared that a visible light telescope can barely detect it at all. Webb was designed specifically to see those objects. It was designed to detect light that has been travelling toward us since the universe was less than 1 billion years old. Webb's primary mirror spans 21 feet across, more than 2.5 times the diameter of Hubble's mirror. It was launched folded inside a rocket fairing and unfolded in space through a sequence of 344 individually motorized deployments, each of which had to succeed for the mission to function. The mirror segments were aligned to tolerances measured in nanometers, fractions of a wavelength of light, while the telescope sat 1 million miles from Earth, where no repair mission could ever reach it. The fact that it worked is, in engineering terms, one of the most precise achievements in the history of the space program. DUIST was proposed in 1989 when the Berlin Wall had recently fallen and the Soviet Union still existed. It was first seriously funded in the late 1990s. It launched in December 2021 when the world was emerging from a pandemic. In the 32 years between concept and launch, 4 American presidents came and went. The internet transformed civilization twice, and a generation of astronomers who had staked their careers on it retired before they could see it operate. That is the timescale of this instrument. The predictions for what Webb would find were specific. They were built on 30 years of accumulated evidence and theoretical confidence. And Webb was the instrument that was finally going to confirm them. It is worth pausing on what it means to say that Webb looks back in time, because the phrase can slide past us without landing. Consider a simpler version of the same idea. When you look at the moon, you are seeing the moon as it appeared approximately 3 seconds ago, the time it takes light to cross the roughly 240,000 miles between the lunar surface and your eyes. When you look at the sun, you are seeing it as it was 8 minutes ago. If the sun vanished right now, you would not know for 8 minutes. The information cannot travel faster than light. At the scale of the solar system, this delay is trivial. At the scale of the universe, it is the central fact of all observational astronomy. When Webb captures light from a galaxy 13 billion light-years away, that light left its source 13 billion years before the telescope existed. The galaxy may look entirely different today. It may have merged with a neighbour, or stopped forming stars, or been torn apart by gravitational forces. We will never know what it looks like now. We can only know what it looked like then, in the moment its light began travelling toward us. Webb was designed to capture those ancient messages, light that had crossed the entirety of the observable universe to reach a mirror 1 million miles from Earth. The age of the universe is 13.8 billion years. Webb can see back to within a few 100 million years of its beginning. The gap between then and the first stars is almost within reach. To understand what Webb found, you first need to understand what we thought we knew. The standard model of cosmology has a name. It is called lambda CDM. Lambda refers to the cosmological constant, a term in the equations of general relativity that represents dark energy, the force that is accelerating the expansion of the universe. CDM stands for cold dark matter, the invisible, non-interacting substance that makes up roughly 27% of all the mass and energy in the universe under current models, and which provides the gravitational scaffolding around which ordinary matter assembles. Together, these two components, dark energy and dark matter, define how the universe is structured and how it evolved. They are the engine and the frame. Everything else, all the stars, all the galaxies, all the planets, every atom in every living body, makes up roughly 5% of the universe's total content. The visible universe, the universe we can see and touch, is a thin layer of complexity sitting on top of a much larger invisible architecture. Under lambda CDM, galaxy formation follows a specific sequence. It is called hierarchical assembly. The idea is that the universe did not produce large structures first. It produced small ones, and those small structures merged over long periods of time into larger ones. Dark matter collapsed into structures called halos, gravitational wells that pulled in hydrogen gas. That gas formed the first stars. Those stars exploded, seeding the surrounding gas with heavier elements. New stars formed from that enriched gas. Those clusters of stars merged with other clusters. Over hundreds of millions to billions of years, this process built up the large galaxies we see today. The timeline is important. The first stars, the first generation of stars, formed from nothing but hydrogen and helium, are thought to have appeared somewhere around 100 to 200 million years after the Big Bang. The first small proto-galaxies emerged after that. The process of assembling those proto-galaxies into something resembling a mature galaxy takes time. It takes many mergers. It takes many stellar generations. Under lambda CDM, the earliest universe should look like a construction site. Small, irregular, chemically simple structures in the early stages of assembly. It should not look like a finished city. For 30 years, every instrument pointed at the distant universe confirmed this picture. The Hubble Deep Field images of 1995 and 1996 showed exactly what the model predicted. A universe at high redshift, filled with small, irregular, blue, active galaxies, messy and young, nothing like the large settled spirals and ellipticals we see nearby. Subsequent surveys refined the picture. Every new telescope added detail. None of them found anything that fundamentally challenged what lambda CDM said the early universe should look like. Consider what that record of confirmation means. Lambda CDM was not accepted because it was convenient or because cosmologists were attached to it. It was accepted because it predicted things that independent observations then confirmed repeatedly across a range of entirely different observational techniques. The acoustic oscillations imprinted in the cosmic microwave background, patterns in the temperature of the oldest light in the universe, matched lambda CDM's predictions with extraordinary precision. The large-scale distribution of galaxies across the sky matched the model's predictions for how matter should have clustered under gravity over cosmic time. The abundance of galaxy clusters at different epochs matched. The ratio of hydrogen to helium in the universe matched the Big Bang nucleosynthesis calculations. Every test confirmed the same framework. This is why the cosmological community was confident. Not arrogant, confident. Confidence built on evidence is not the same thing as assumption. Lambda CDM had earned its status. Every telescope before Webb had confirmed the model. The depth of that confidence deserves to be understood on its own terms. Lambda CDM is not a model that has survived because it was convenient, or because alternatives were unavailable, or because the cosmological community is resistant to revision. It survived because it made predictions that independent, unrelated observations repeatedly confirmed. Consider a few of them. The model predicts a specific ratio of hydrogen to helium in the universe based on the conditions of the first few minutes after the Big Bang, when protons and neutrons were fusing under extreme heat and density. Observations of hydrogen and helium across the universe match that prediction. The model predicts the existence of acoustic oscillations, pressure waves that propagated through the hot plasma of the early universe before it cooled and froze, and the specific angular scale at which those oscillations should appear in the cosmic microwave background. The Planck satellite measured those oscillations with extraordinary precision, and they match. The model predicts the large-scale distribution of galaxies across the sky, the way they cluster into filaments and sheets and voids, and surveys of hundreds of thousands of galaxies match that predicted distribution. These are not related measurements. They probe completely different physical phenomena across different timescales. When every probe of a different phenomenon returns the same answer, the framework producing that answer is not held on faith, it is held on evidence. Webb was supposed to confirm it further. The plan was not discovery in the sense of surprise. The plan was precision, making the confirmed picture sharper. When Webb's first deep field image released on July 11, 2022, the scientists who built the model were not prepared for what they saw. The image released on July 11, 2022, contained more distant galaxies in one frame than Hubble could photograph in weeks of exposure. That sentence is not an exaggeration. Hubble's famous deep field image, taken in 1995, required 10 consecutive days of observation. The telescope pointing at a single patch of sky, roughly the size of a grain of sand held at arm's length, to capture approximately 3,000 galaxies. Webb's first deep field covered similar territory in a fraction of the exposure time and captured detail at redshifts Hubble could not reach at all. The image was released at a White House briefing. It was described as the deepest infrared image of the universe ever taken. Every galaxy visible in it, and there were thousands, was a message in light that had been travelling for billions of years before reaching the mirror of a telescope that had not existed when much of that light began its crossing. For a few days, the scientific community reacted with something close to celebration. The images were distributed across every major news outlet in the world. Cosmologists wrote detailed threads explaining what was visible. Webb's optical systems had deployed without error. The mirror had aligned to its design tolerances. The telescope was at its orbital position, 1 million miles from Earth, operating in an environment of extreme cold, and it was working exactly as designed. And the early universe was there. It was visible. The redshift range that Lambda CDM had predicted would show the first generations of galaxies was accessible for the first time at this level of sensitivity. The confirmation, everyone assumed, was about to begin. Here is what those first images did not say, that everything was fine. Then the data started to be analysed. In the weeks following the first image release, the teams working on Webb's early data noticed something that did not fit. Among the candidate high redshift objects, the objects in the image that appeared to be at the distances corresponding to the early universe, several were unexpectedly bright. To understand why brightness at that distance is alarming, you need to understand the relationship between brightness and mass. A galaxy that contains more stars shines more light. More stars means more stellar mass. A galaxy that is bright at a distance of 13 billion light-years is a galaxy that, 13 billion years ago, already contained an enormous number of stars. Under Lambda CDM, early galaxies should be faint not because the universe was somehow dimmer then, but because the galaxies were genuinely smaller. They had not yet had time to accumulate the stellar populations that make today's large galaxies shine. A young galaxy at high redshift should look, in Webb's images, like a dim, compact smudge. Several of the objects in Webb's early data were not dim, compact smudges, they were bright. Bright enough that their implied stellar masses, calculated from their brightness and confirmed distance, placed them far outside the range the model predicted. Brightness at that distance means mass. A galaxy at redshift Z greater than 10, meaning we are seeing it as it existed less than 500 million years after the Big Bang, should be relatively small and faint under the standard model. The model's predictions for what high redshift galaxies should look like are not vague. They are specific numerical predictions for how many such galaxies should exist in a given survey area, how bright they should be, how massive they should be, and how their properties should distribute across the population. The initial reaction among the teams was cautious. Photometric redshift estimates, which calculate how far away something is based on the colour of its light, without taking a full spectrum, are not always reliable. Bright anomalies at extreme distances could be closer objects that had been misidentified. The team set about getting spectroscopic confirmations, full measurements of the light spectrum that pin down the redshift precisely. One of the first results to come back with a confirmed spectroscopic redshift was the object that the team named Maisie's Galaxy, named by astronomer Stephen Finkelstein at the University of Texas at Austin for his daughter, on her birthday when the result came back. Maisie's Galaxy had a confirmed spectroscopic redshift of approximately 11.4. That number translates to a look-back time of roughly 13.4 billion years. We are seeing that galaxy as it existed approximately 390 million years after the Big Bang. Let that sink in for a moment. To put 390 million years in perspective, the universe was 390 million years old when Maisie's Galaxy existed. The universe today is 13.8 billion years old. That galaxy existed when the universe had completed less than 3% of its current age. Under lambda CDM, a galaxy at that age should not have the stellar mass Maisie's Galaxy appears to have. The model allows for small proto-galactic structures at that epoch, the first stirrings of hierarchical assembly. What it does not allow for is a system that has already assembled significant stellar mass and shows the structural properties of a galaxy that has been forming stars for an extended period. Not one unusual galaxy, not 5, dozens, and more appearing with each new field. The galaxies were there, they were bright, they were massive, and under everything we thought we knew about the early universe, they should not have been able to exist. Maisie's Galaxy was the first name most people heard, but it was not the only one that did not fit. In February 2023, astronomer Ivo Lab and his team at Swinburne University of Technology published a paper in the journal Nature. It was not a paper about one galaxy. It was a paper about 6 candidate galaxies found in Webb's early data, all at redshifts placing them in the first 700 million years of cosmic history. The team estimated the combined stellar mass of these 6 objects, the total number of solar masses they represented in accumulated stars, and arrived at a figure that stopped the community. The combined stellar mass of those 6 candidate galaxies was comparable to the Milky Way. Our galaxy, the Milky Way, took roughly 10 billion years to assemble its current stellar population of somewhere between 100 and 400 billion stars. These 6 objects appeared to have assembled comparable mass in a fraction of that time, in a universe that had barely had time to produce its first generation of stars. Let that sink in. The team called them the Cosmic Monsters. The name was not chosen casually. Each galaxy individually would have been a significant anomaly. 6 of them in a single survey field, discovered within months of Webb beginning science operations, was a result that demanded a serious response. Separately, another team was examining an object catalogued as GS9209. It sits at a redshift of approximately 4. 7, meaning we see it as it existed roughly 1.3 billion years after the Big Bang. GS9209 is not merely massive for its age, it is quenched, a term astronomers use for a galaxy that has stopped forming stars. A quenched galaxy is one that has gone through its entire active star-forming phase and then shut down, transitioning from a system ablaze with new stars to a cold, settled collection of aging stellar populations. Under the standard model, quenched galaxies at that mass and that redshift are, under current model predictions, not possible. To quench, a galaxy must first form, accumulate mass, trigger the mechanisms that shut off star formation, typically intense feedback from a central supermassive black hole, and then settle into a passive state. GS 9209 appears to have done all of that in a period when the universe was barely old enough to have allowed the process to begin. When the universe was barely old enough to have allowed the process to begin. A quenched galaxy is in some ways more alarming than a merely large one. A large galaxy could, in principle, form quickly if you give it enough gas and enough time to compress it into stars. But a quenched galaxy has already done something more complex. It assembled, it burned brightly through an active star-forming phase, and then it stopped, meaning some process shut down its gas supply or expelled what remained. The shutdown mechanism in large galaxies is typically the central supermassive black hole, which at high accretion rates drives powerful winds capable of clearing gas from the entire galaxy. For GS 9209 to be quenched at redshift 4.7, it needed to have not only assembled its stellar mass, but also grown a central supermassive black hole large enough and active enough to terminate star formation, and then to have gone quiet, all of that, in a universe that was 1.3 billion years old. The implication chain here is worth following step by step, because it clarifies why these objects are not merely curious outliers. First, if these galaxies exist at the masses and redshifts Webb is measuring, then the matter required to build them, the hydrogen gas, the dark matter halos, the stellar populations, must have been assembled in the early universe. That matter had to come from somewhere. It had to collapse, form stars, and accumulate into galaxy-scale structures within the available time window. Second, the available time window under lambda CDM does not provide enough opportunity for matter to collect, collapse, and assemble at the rates these galaxies imply. The density fluctuations in the early universe, the tiny variations in mass distribution that seeded all later structure, were small. Structure grew slowly from the bottom up. The math of hierarchical assembly, applied to the conditions of the early universe as lambda CDM describes them, does not produce objects this massive this early. Third, if the math does not produce them, and yet they exist, then one of two things is true. Either the observations are wrong, or the math is wrong. The spectroscopic confirmations ruled out the simplest version of the first option. These were not photometric errors, not redshift misreadings, not outliers in a thin data set. Consider what spectroscopic confirmation means in practice. When Webb observes a distant galaxy, its camera collects all the light arriving from that object at once, producing an image. But when the spectrograph, called near spec, observes the same object, it spreads that light out into its component wavelengths, the way a prism spreads white light into a rainbow. Each chemical element, when heated to the temperatures of a stellar atmosphere, emits and absorbs light at precise, characteristic wavelengths. Hydrogen emits at specific wavelengths. Oxygen emits at others. Carbon, silicon, magnesium, each at their own. These spectral lines are like fingerprints. When they are shifted from their laboratory measured positions, the shift is directly proportional to how fast the galaxy is receding, which is directly proportional to its distance. A spectroscopic redshift is not an estimate. It is a precise measurement. The galaxies are where they appear to be. The distances are not in question. They were the data. The question is not only what Webb found. The question is when. Time is not a detail in this story. It is the central constraint. Everything in the standard model of galaxy formation is governed by time, by how much of it was available at each stage of the universe's development, and by how quickly the physical processes that build structure can operate. To understand why the Webb findings are so difficult to accommodate, you need to understand what those physical processes require. The universe as it emerged from the Big Bang was almost perfectly smooth. There were tiny variations in density, regions that were fractionally denser than their surroundings, regions that were fractionally less dense. The scale of those variations was tiny, roughly 1 part in 100,000. Those tiny differences were the seeds of everything that followed. Over time, gravity amplified them. The denser regions pulled in more matter. They grew. Eventually they collapsed into the first structures. But gravity operates on a timescale set by the density of matter and the distances involved. In the early universe, the relevant timescale for the first dark matter halos to collapse was millions of years. For those halos to pull in enough gas to begin forming stars, more time. For the first stars to live out their lives, explode as supernovae, and enrich the surrounding gas with heavier elements, more time again. The most massive stars, the ones responsible for the heaviest elements, live for only a few million years. But less massive stars, the ones that constitute the bulk of stellar populations, live for tens of millions to billions of years. For a second generation of stars to form from enriched gas, for stellar clusters to assemble, for clusters to merge into protogalaxies, for protogalaxies to merge into larger galaxies, each step required time, and the steps could not be skipped. Under lambda CDM, the earliest galaxies at redshifts above 10, meaning galaxies that existed less than 500 million years after the Big Bang, should be in the early stages of this process. The model is specific about this. At redshift z equals 10 or higher, the universe was approximately 460 million years old. Lambda CDM predicts that the most massive galaxies at that epoch should contain stellar masses on the order of 100 million to at most a few billion solar masses. Smaller than what we see today, by a large factor, because they simply had not had enough time to accumulate more. Maisie's galaxy, confirmed at redshift 11.4, exists at roughly 390 million years after the Big Bang. At that age, under the standard model, it should hold stellar mass in the range of a few 100 million solar masses. It appears to hold several billion. The cosmic monsters, at redshifts between 7 and 10, exist in a window spanning roughly 700 to 1100 million years after the Big Bang. Their estimated stellar masses range from tens of billions to potentially more than 100 billion solar masses. And then there is GS 9209. Consider what those numbers require. The Milky Way accumulated its stellar mass over roughly 10 billion years. The cosmic monsters appear to have accumulated comparable mass in less than 1 billion years, and some of them in far less. The ratio of mass accumulated to time available, if the redshift estimates are correct, demands a pace of star formation that has no observed equivalent anywhere in the universe, at any epoch, that we have ever studied. To accumulate that mass in the available time, the rate at which those galaxies converted gas into stars would have to be extraordinarily high. Astronomers measure this as the star formation efficiency, the fraction of available gas that gets converted into stars rather than blown away by stellar winds, radiation pressure, and the explosive force of dying stars. In galaxies we observe today, this efficiency is typically around 1 to 10%. Most of the gas available for star formation never becomes a star. It gets disrupted. For the cosmic monsters to exist as measured, the star formation efficiency in the early universe would have to be dramatically higher than anything we have ever observed elsewhere. Some estimates, applying the available time window and the required stellar mass accumulation arrive at efficiencies close to or above 100%. That number is not a model parameter to be adjusted. It is a wall. You cannot convert more gas into stars than you have gas. You cannot convert more gas into stars than you have gas. Let that sink in for a moment. The number the model requires does not merely strain physics, it breaks it. There is a way to feel the scale of this constraint. The Milky Way today contains somewhere between 100 and 400 billion stars. It has been forming those stars over roughly 10 billion years. If you average that out, a simplification, but a useful one, the Milky Way has been producing somewhere in the range of 10 to 40 billion stars per billion years of its history. The cosmic monsters, under the most challenging estimates, appear to have produced comparable stellar populations in less than 1 billion years. That means their star formation rate, if the mass and redshift estimates are correct, would have to be 10 to 100 times higher than the Milky Way's average, sustained, not momentary, during a period when the available gas supply was itself limited by what the early universe could provide. Star-forming galaxies today, even the most intensely active starburst systems, do not approach anything like that rate, while also maintaining the structural characteristics that Webb observes in these objects. The numbers are not merely unusual, they are outside the range of what any observed galaxy at any epoch has ever demonstrated. There is a version of this problem that scientists have been willing to call a statistical fluke. Some scientists argued these galaxies might be exceptionally rare, the tail end of a distribution that lambda CDM allows to exist in small numbers. But the number of them appearing in Webb's surveys does not support the rare exception interpretation. Rare exceptions appear rarely. What Webb was finding appeared repeatedly, in field after field, in survey after survey, at numbers that exceeded the model's predictions not by 1% or 2%, but by factors that left the rare exception framing without statistical support. The time problem alone would be enough to demand a serious rethinking of the model. But the time problem is not the only problem. There is a second strand of the problem, and in some ways it is harder to argue away than the timing. When the Big Bang occurred, the matter it produced was simple. The universe emerged from that first moment containing hydrogen, the lightest element. A single proton orbited by a single electron. It contained helium, the second lightest, assembled from 2 protons and 2 neutrons in the first few minutes of cosmic time. It contained trace amounts of lithium, the third lightest. That was the entire periodic table of the early universe. Hydrogen, helium, lithium, and almost nothing else. Every element heavier than lithium. Every atom of carbon, oxygen, nitrogen, iron, silicon, magnesium, calcium. Every element that makes up a rocky planet, every element that makes up a living cell, was made inside a star, or in the violent death of a star, or in the collision between 2 dead stars. This process is called stellar nucleosynthesis, and it operates on a specific timescale. A massive star, the kind capable of producing the heaviest elements in its core and distributing them outward in a supernova, lives for a few million years. A less massive star lives longer, but produces lighter elements. The heaviest elements of all, the gold and the platinum and the uranium, are produced in the merger of 2 neutron stars, the collapsed cores of stars that have already lived and died. For those mergers to happen, you first need 2 separate massive stars to form, live their lives, collapse, and become neutron stars in the same gravitational system, and then for those 2 neutron stars to spiral together over an additional period of time. Gold, in this sense, is not the product of a single stellar event. It is the product of a sequence. Gold, in this sense, is not the product of a single stellar event. It is the product of a sequence. The gravitational wave detectors LIGO and Virgo confirmed this in 2017, when they detected the merger of two neutron stars in a galaxy 130 million light-years away. The optical afterglow of that merger, monitored by telescopes around the world in the days that followed, showed spectroscopic signatures consistent with the rapid production of heavy elements including gold, platinum and lanthanides. That single event was estimated to have produced gold at a quantity roughly 10 times the mass of the Earth. Let that sink in for a moment, which sounds large, until you consider that the universe contains hundreds of billions of galaxies, each containing hundreds of billions of stars, and that gold is still one of the rarest elements in the cosmic abundance table. The rarity of gold is, in part, a record of how rarely the precise sequence of events required to produce it. Two massive stars forming in the same system, both living and dying. Their remnant cores spiraling together has been completed across cosmic time. A galaxy in the first 400 million years of the universe finding heavy element signatures in its spectra is a galaxy that has already completed that sequence multiple times, at a pace that nothing in the subsequent history of the universe appears to have matched. Consider what this means for the timeline of the early universe. For a galaxy in the first few 100 million years after the Big Bang to contain heavy elements in significant quantities, carbon, oxygen, silicon, iron, the elements that make stars look chemically mature when their light is analysed, it must have already hosted at least one prior generation of stars. Those stars had to form from the initial hydrogen gas, live their lives, and explode or merge, seeding the surrounding gas with the products of their nuclear burning. Only then could a second generation of stars form from that enriched material. But adding a prior generation of stars to the timeline does not merely add a few extra millions of years to the clock. It adds the full sequence: gas collapse, star formation, stellar lifetimes ranging from millions to tens of millions of years, stellar deaths, and the explosive distribution of heavy elements through the surrounding medium, cooling of that medium, recollapse into the next generation. Each of those steps takes time. Each of them has physical minimum durations that are set by the relevant rates: gravity, nuclear burning, gas cooling, and those rates were determined by the conditions of the early universe. In 2023, Webb obtained spectra of galaxies in the redshift range corresponding to the first billion years of cosmic history, and found signatures of carbon and oxygen, elements that require multiple stellar generations to produce in significant quantities in objects that, under Lambda CDM's timeline, should barely have completed their first generation of star formation. The spectrograph on Webb, called NearSpec, breaks incoming light into its component wavelengths with sufficient precision to identify the signatures of specific atomic transitions. Carbon and oxygen leave specific fingerprints in those spectra. Those fingerprints were there. The carbon and oxygen were there. They had to come from somewhere. The somewhere required time that the model says was not available. What this means, when placed alongside the time problem from the previous strand, is something with a specific logical structure. The galaxies are not merely too massive too early. They are also too chemically evolved too early. The time problem alone would require the model to explain an anomaly in stellar mass accumulation. The metallicity problem requires the model to also explain an anomaly in chemical evolution, an anomaly that demands even more time, because it requires the mass anomaly to have been completed and then run again through an entire additional stellar generation. You cannot have the chemical enrichment without first having the mass assembly. And you cannot have the mass assembly twice, once for the first generation and once for the second, in the time the model provides for it once. Each strand of the problem, the timing, the mass, the chemistry, would challenge the model alone. Together, they do something else entirely. When a single measurement contradicts a model, science calls it an anomaly. An anomaly is interesting. An anomaly gets written up in a paper, it gets checked, it gets debated. Most of the time, one of three things happens. The measurement turns out to have been wrong, or the model absorbs the anomaly as an edge case within its existing range, or the anomaly sits unresolved on a list of open questions while the rest of science moves forward. Single anomalies rarely break models. Models are robust enough to contain them. When 10 measurements contradict a model, science pays closer attention. When hundreds of independent measurements, taken across multiple survey programs by multiple teams using multiple instruments, all point to the same discrepancy, and when that discrepancy does not diminish as the data gets better, but instead gets more pronounced, science has moved out of anomaly territory entirely. The lab it all. Paper in Nature was one data point. It attracted immediate and serious attention, but within months of its publication, independent teams running their own analysis of Webb data were arriving at similar conclusions. The SEERS survey, the Cosmic Evolution Early Release Science Survey, identified numerous high redshift galaxy candidates independently. The JADE survey, the JWEST Advanced Deep Extragalactic Survey, went deeper still, probing the universe at redshifts that had been almost entirely inaccessible before Webb. The GLASS survey contributed further candidates. Each of these programs operated independently, with their own teams, their own analysis pipelines, their own systematic error checks, and their own photometric calibration procedures. The overabundance of massive early galaxies relative to what lambda CDM predicts is not a number that emerged from one team's analysis or one telescope's calibration. Across multiple studies, the factor by which the observed number of massive early galaxies exceeds the model's prediction falls somewhere in the range of 10 to 100 times, not 10 to 100% above predictions. 10 to 100 times the predicted number. That is not an error bar. That is not a calibration issue. A factor of 10 discrepancy means the model is predicting one galaxy for every 10 that Webb finds. A factor of 100 means the model is predicting one for every 100. Let that sink in. To understand the magnitude of that gap, consider an analogy. If you are baking and you expect a cake to rise to 2 inches in the oven, and it rises instead to 20 inches, 10 times the prediction, you do not conclude that you slightly miscalibrated your oven temperature. You conclude that something in the fundamental process is different from what you assumed. A 10 times discrepancy in a well-characterized system is not a measurement error. It is a sign that the model of the system is missing something significant. Garth Illingworth, an astronomer at the University of California, Santa Cruz, who has spent decades studying the distant universe with Hubble and was among those working with early Webb data, described the results in terms that captured the controlled alarm spreading through the community. The observations were, in his words, way outside the box. That phrase, from a scientist who has spent a career working at the edges of what telescopes can see, carries weight that a less measured description might not. Scientists who describe their own field's findings as way outside the box are not being rhetorical. They are reporting what the numbers show. This is not the first time cosmology has found a tension between model and observation that was large enough to demand attention. The Hubble tension, the discrepancy between two different methods of measuring how fast the universe is currently expanding, has been growing for years. One method measures the expansion rate using the cosmic microwave background, the oldest light in the universe, and arrives at a specific number. A second method measures the expansion rate using the distances to nearby galaxies, and arrives at a different number. They should agree. They do not. The gap between them has widened as measurements have become more precise, not narrowed. Some cosmologists have proposed that the Hubble tension is a signal that lambda CDM is incomplete in its treatment of the universe's expansion history. The early galaxy problem is a separate discrepancy, in a separate domain, measured with a separate instrument. Two large, persistent, well-confirmed discrepancies pointing in the same direction toward a framework under stress is a different situation than one. Two large, persistent, well-confirmed discrepancies pointing in the same direction toward a framework under stress is a different situation than one. The Hubble tension deserves a brief explanation because it illuminates why the early galaxy problem is being taken as seriously as it is. Two completely independent methods of measuring the universe's current expansion rate, called the Hubble constant, produce different numbers. One method analyzes the cosmic microwave background and extrapolates forward using lambda CDM's equations. The other measures the distances to nearby galaxies directly, using a chain of calibrated distance indicators. Both methods are carefully executed by independent teams using independent instruments. The Hubble constant value from the CMB analysis is approximately 67 kilometers per second per megaparsec. The value from local measurements is approximately 73. They should agree. They do not. The discrepancy has been growing more significant as both measurements have become more precise, not less. Some cosmologists believe the Hubble tension will eventually be explained by systematic errors. Others believe it is pointing toward a genuine incompleteness in the model. That debate has been running for years. The early galaxy problem now runs alongside it. When a model is tested against reality and the results come back 10 to 100 times outside its predictions, across multiple independent programs with spectroscopic confirmation, and when a second independent discrepancy has been accumulating in parallel, science has to choose a word for what is happening. The word that has appeared in the peer-reviewed literature used by the researchers who built and defended lambda CDM is not interesting. It is not surprising. The word is crisis. This is the point where science stops calling something a surprise and starts calling it a crisis. There is a natural place the mind goes when confronted with data this uncomfortable. It goes toward the instruments. If the results are this far outside predictions, then the telescope is measuring something incorrectly. Webb's photometry, its measurements of how bright these objects are, could be systematically off in a way that makes distant objects look more massive than they are. The redshift estimates for at least some of these candidates could have placed them at the wrong distance. There could be a class of objects that looks like a massive early galaxy but is something else entirely. A bright quasar, a gravitational lens, a misidentified foreground object. These are not irrational responses. They are the correct responses. In science, when a result seems impossible, the first obligation is to look hard for the error. The teams working on Webb data have done exactly that, and it is worth spending some time on what they've found, because the process of ruling out the instrumental explanations is what makes the remaining problem so difficult to avoid. The photometric error question was addressed directly. Webb's photometric calibration, the precision with which it measures the brightness of objects, has known uncertainties. Those uncertainties have been published, characterized, and applied to the early data. When applied to the mass estimates for the cosmic monsters and similar objects, the calibration uncertainties can shift the mass estimates, but they do not shift them enough to bring the most extreme cases into agreement with the model. The most careful analyses, accounting for the full range of photometric error, still arrive at stellar masses that exceed what lambda CDM permits at those redshifts. The calibration uncertainties are real, but they are not large enough to close a gap of this magnitude. The redshift question was addressed by spectroscopic follow-up. Photometric redshifts, estimates based on colour alone, measuring how far the galaxy's spectral energy distribution has shifted toward the red end of the spectrum, can be wrong. They are estimates, and estimates have ranges. But spectroscopic redshifts, which measure the precise wavelengths of known atomic emission lines in an object's spectrum, are not subject to the same ambiguities. Maisie's galaxy has a spectroscopic redshift. GS 9209 has a spectroscopic redshift. Multiple of the most extreme early galaxy candidates have been spectroscopically confirmed by independent teams using ground-based instruments at the Very Large Telescope and Keck Observatory. The distances are not measurement errors. Now consider what the numbers require. A factor of 10 discrepancy between model prediction and observation means that the photometric calibration errors would need to be biased in the same direction across every galaxy in every independent survey by an amount roughly an order of magnitude larger than the known error budget. The calibration would have to be wrong by more than it is known to possibly be wrong. That is not a calibration correction, that is a different telescope. A factor of 100 discrepancy would require the calibration to be wrong by 2 orders of magnitude. At that point, the argument is no longer about error margins. It is about whether the instrument is functioning at all. And the instrument is, by every other metric, functioning exactly as designed. Science revises models. This is true, and it is one of the things that distinguishes science from other systems of understanding. Prior corrections to lambda CDM have been real and important. The discovery that the expansion of the universe is accelerating, announced in 1998 by 2 independent teams studying distant supernovae, work that earned Saul Perlmutter, Brian Schmidt, and Adam Ries the Nobel Prize in Physics in 2011, required adding the cosmological constant to the model. That was a significant revision. The Hubble tension has prompted ongoing work on how the expansion rate is calculated. These kinds of revisions happen, models absorb them, but there is a difference between a parameter adjustment and a structural problem. A parameter adjustment shifts a number within a framework that otherwise remains intact. A structural problem means the framework itself is generating wrong predictions, not because a number is slightly off, but because the underlying assumptions about how things work are insufficient to describe the reality being observed. The overabundance of massive early galaxies is not asking for a parameter to move. It is asking for an explanation of why the universe assembled structure so much faster than the model says it could. The data is what it is. The question now is what to do with a map that no longer matches the territory. This is not the first time cosmology has found itself holding a model that reality refused to fit. For roughly 1500 years, the dominant model of the solar system placed Earth at the centre of everything. The model was not primitive or uninformed. It had been developed and refined by some of the most careful observers in the ancient and medieval world, by Ptolemy in the 2nd century, by Islamic scholars in the medieval period who corrected and expanded his calculations, by European astronomers who built on their work. It incorporated epicycles, small circles within larger orbits, to account for the observed wandering paths of the planets as seen from Earth. With enough epicycles, the model could predict planetary positions well enough to be practically useful for navigation and calendar making for centuries. It was tested against observation continuously. It held together not because people were credulous, but because it worked within the limits of what was observable. Then Copernicus published his heliocentric model in 1543, and Kepler derived the elliptical orbits, and Galileo's telescope started producing observations that the geocentric model could not accommodate. The model did not collapse overnight. The transition from geocentric to heliocentric understanding took more than a century, and involved not only astronomical debate but philosophical and institutional resistance. But what replaced the geocentric system was not a rejection of the observations that had supported it. It was a larger framework that explained all the same data, plus the new data that the old model could not contain. In the 20th century, Fred Hoyle argued for a steady-state universe, one that had no beginning, that had always existed, and that maintained a constant overall density as new matter was continuously created to fill the space left by expansion. Hoyle was one of the most brilliant cosmologists of his generation. The steady-state model was elegant. It avoided the philosophical difficulties of a creation event. It had serious defenders. In 1965, two engineers at Bell Labs in New Jersey named Arno Penzias and Robert Wilson, trying to eliminate a persistent microwave noise in an antenna they were testing, discovered that the noise was coming from everywhere in the sky equally, at the same intensity in every direction they pointed. What they had found was the cosmic microwave background, the faint thermal afterglow of the Big Bang itself, filling the entire sky at a temperature of 2.725 degrees above absolute zero. The steady-state model had no explanation for it. The Big Bang model had predicted it years earlier. The steady-state model was not revised. It was replaced. The steady-state model was not revised. It was replaced. What is often forgotten about these transitions is how complete the confidence was before they happened. Ptolemy's geocentric model was not a rough sketch. It was a precise predictive system that astronomers used for navigation, calendar calculation, and eclipse forecasting for 15 centuries. The people who used it were not credulous. They were careful. The model worked within the limits of what they could observe. When the limits of observation expanded, when the telescope arrived, the model's failures became visible. The same is true of Newton. His mechanics were not merely popular. They were the most precisely confirmed physical theory that had ever been developed, tested against planetary orbits measured to within fractions of an arcsecond. The precession of Mercury's perihelion, the tiny discrepancy that eventually demanded general relativity, was measured at 43 arcseconds per century. That is an angle roughly equal to the apparent width of a human hair held at arm's length, accumulated over 100 years. It took instruments precise enough to measure that angle reliably before the discrepancy even became visible. The lesson is not that prior scientists were wrong to be confident. The lesson is that confidence based on the limits of available instruments is not the same as confidence based on the limits of reality. Webb has extended the limits of available instruments further than they have ever been extended in the direction of cosmic time. Isaac Newton's mechanics governed celestial motion for more than 200 years. They were tested by every astronomical observation available, applied to the orbits of planets and the trajectories of comets. They were accurate to the limits of every instrument used to test them. Then, in the early 20th century, the perihelion of Mercury, the point in Mercury's orbit closest to the Sun, was found to shift over time by a tiny amount that Newton's equations could not explain. It was a small discrepancy, in absolute terms. But it was real, and it persisted as instruments improved. Einstein's general theory of relativity, published in 1915, predicted exactly the observed precession. Newton's mechanics turned out to be a limiting case of a more complete description, accurate under most conditions, but insufficient at the extremes. The pattern is consistent across all of these cases. Every time a model has broken in physics, the replacement has not discarded what the old model got right. It has expanded the framework to include what the old model could not accommodate. And in every case, the trigger was the same, an instrument precise enough to detect a discrepancy that the model had not predicted. Ptolemy's model held until telescopes showed Jupiter's moons in orbits that did not center on Earth. Newton's mechanics held until measurements precise enough to detect Mercury's precession demanded an explanation Newton's equations could not provide. The steady-state universe held until an antenna sensitive enough to detect the cosmic microwave background registered the afterglow of an event the model said never happened. Lambda CDM is not a mistake. It is the best tested cosmological framework in history. And it may be standing where Newton stood in 1914, not at the end of knowledge, but at a boundary it did not know it had. The scientists who built the standard model are not defending a mistake. They are standing at the edge of something larger. The first place scientists looked for a solution was the one ingredient in the model that nobody fully understands. Dark matter is not a hypothesis anymore. Its effects have been measured in galaxy rotation curves. The observation that the outer regions of galaxies rotate at speeds that cannot be explained by the visible matter alone. It has been measured in the gravitational lensing of background light, the bending of light from distant objects by the mass of intervening galaxy clusters, where the lensing is far stronger than the visible matter can produce. It has been confirmed in the temperature patterns of the cosmic microwave background, which bear the imprint of acoustic oscillations in the early universe that match what lambda CDM predicts only if roughly 5 times as much dark matter as ordinary matter was present. Under current models, dark matter constitutes roughly 27% of all the mass and energy in the universe. It has been confirmed indirectly by dozens of independent methods. What has not been found, what has resisted every direct detection experiment, from underground particle detectors to gamma-ray satellites to collider searches, is what dark matter is at the particle level. In lambda CDM, dark matter is assumed to be cold. Cold, in this context, is a technical term. It does not refer to temperature in the everyday sense. It means that dark matter particles move slowly relative to the speed of light, slowly enough that they could not have streamed out of the overdense regions in the early universe before structures had a chance to form. Cold dark matter clumps readily under gravity. It forms halos efficiently. It provides the gravitational scaffolding that the model needs to explain the large-scale structure of the universe as we observe it today. But cold dark matter also sets a pace for structure formation. Because cold dark matter halos grow hierarchically, smaller ones forming first, merging into larger ones over time, the pace at which galaxies can assemble is tied to the rate at which dark matter halos of sufficient mass become available. And that rate in the standard cold dark matter scenario is too slow to explain the cosmic monsters. One proposed solution is to change what the dark matter is. Warm dark matter consists of particles that move somewhat faster than cold dark matter, not freely streaming out of density concentrations, but mobile enough to smooth out the smallest scale fluctuations in the early universe. Because warm dark matter particles are more mobile, they suppress the formation of the smallest structures. This changes the history of halo assembly in ways that could, in principle, allow more mass to concentrate into fewer, larger halos earlier. Fuzzy dark matter takes this logic further. It consists of ultralight particles, possibly axions with masses around 10 to the power of minus 22 electron volts, that behave more like a quantum wave than a classical particle. The wave-like nature of fuzzy dark matter creates a characteristic scale below which structure formation is strongly suppressed, potentially allowing different behavior at small scales while preserving lambda CDM's successes at large scales. Primordial black holes that formed in the first fractions of a second of cosmic time, before any stars or galaxies existed, have been proposed as dark matter candidates that could seed early structure formation directly, providing massive gravitational anchors around which the first galaxies could assemble more quickly. Teams at several institutions have run simulations using modified dark matter physics to see whether these alternatives can produce the early galaxy population that Webb observes. Some simulations, with optimistic assumptions about the dark matter properties, can push galaxy formation earlier and produce more massive early structures than the standard cold dark matter scenario allows. A few produce results that, at the high end of their uncertainty ranges, begin to approach what Webb finds. None of them fully close the gap. The most extreme Webb findings remain outside what even modified dark matter scenarios produce. Warm dark matter and fuzzy dark matter can accelerate early structure formation to a degree, but the acceleration is not large enough, in current simulations, to account for galaxies as massive as the cosmic monsters at the redshifts where they appear. Primordial black holes as dark matter seeds face the constraint that direct searches for primordial black holes in various mass ranges have not detected them, and the mass ranges most useful for seeding early galaxies overlap with ranges that are tightly constrained by observations of gravitational wave events and microlensing surveys. There is a deeper constraint that applies to all modified dark matter proposals. Any modification to dark matter physics must not only explain the early galaxy problem, it must continue to explain everything that cold dark matter already explains correctly. The large-scale structure of the cosmic web, the abundance of galaxy clusters at lower redshifts, the acoustic oscillations in the CMB, the distribution of satellite galaxies around large host galaxies. All of these were tested against cold dark matter and found to be consistent. A replacement framework cannot fix the early universe and break everything else in the process. If dark matter alone cannot explain what Webb found, then the problem may not be in the matter at all, but in what happened before the first matter formed. If dark matter alone cannot explain what Webb found, then the problem may not be in the matter at all, but in what happened before the first matter formed. The absence of a direct detection of dark matter particles after decades of increasingly sensitive experiments is itself a data point. Underground detectors designed to register the rare collision between a dark matter particle and an atomic nucleus have grown steadily more sensitive over the years. None of them have detected a signal. Particle collider experiments have searched for evidence of dark matter production at high energies. None of them have found it. This does not prove dark matter does not exist. The indirect evidence for its gravitational effects remains solid, but it has narrowed the range of what dark matter can be, and some of the most naturally simple candidates, the ones that would have been most convenient for particle physicists, have been ruled out. The difficulty of finding a dark matter modification that both accelerates early galaxy formation and survives all the constraints from non-detection experiments is real. The second response track begins with a number that most people have never heard of: the star formation efficiency. It is, in some ways, the most quietly radical of the three response tracks, because it does not require new particles or new fundamental laws of physics. It requires only that the process of turning gas into stars was, in the early universe, far more effective than it is anywhere we have ever observed. Start with what we know about how stars form. A galaxy contains gas, vast clouds of hydrogen and helium mixed with whatever heavier elements previous stellar generations have contributed. Some of that gas is in regions dense enough and cold enough to collapse under its own gravity and ignite nuclear fusion, but most of it is not. Most of it is heated, stirred and dispersed by the radiation and explosive force of the stars that do form. massive stars radiate such intense ultraviolet light that they ionize the gas around them, creating regions of hot plasma that cannot further collapse. When those massive stars end their lives in supernovae, the shockwave heats and disperses the surrounding gas over distances of hundreds of light years. Active black holes at galaxy centers drive powerful jets and winds that can push gas out of the galaxy entirely. Supernovae from stellar clusters heat the interstellar medium, raising its pressure and preventing the collapse of cold gas clouds that would otherwise have formed new stars. All of these processes, stellar radiation, stellar winds, supernova feedback, black hole feedback, work against star formation. They are not incidental nuisances. They are part of what regulates how galaxies grow and evolve. Without them, galaxies would convert their gas into stars far faster than they do. The fact that galaxies contain both stars and gas at the same time, in rough proportion, is itself evidence that these feedback processes are operating on a continuous basis. This is what gives us the star formation efficiency figure. In ordinary galaxies today, across decades of observation, with every available instrument, star formation efficiency is typically between 1 and 10%. Occasionally it reaches somewhat higher in dense starburst environments, galaxies undergoing exceptionally intense periods of star formation triggered by mergers or tidal interactions. But even in those cases, the efficiency does not come close to exhausting the available gas. For the cosmic monsters to exist with the masses Webb observes, in the time available, the star formation efficiency in the early universe would have to be dramatically higher than anything in that range. Some of the most careful calculations, working backward from the observed stellar masses and the available time window, require efficiencies approaching 50% in the most extreme cases. A few analyses push the implied efficiency higher still. The simulations that try to produce these efficiencies are among the most computationally sophisticated in astrophysics. FIRE, Feedback in Realistic Environments, is a simulation framework developed by teams at Caltech, Carnegie Observatories, and several other institutions, designed to model the detailed physics of stellar feedback at high resolution. Illustris TNG is a large-scale cosmological simulation run by teams at the Max Planck Institute for Astrophysics, MIT, Harvard, and other institutions that tracks the evolution of galaxies across cosmic time. Both frameworks have been updated specifically to explore whether modifications to how stellar feedback is implemented can push early galaxy formation toward the masses Webb observes. Early results suggest that, with specific assumptions about how feedback operated in the early universe, the gap can be partially narrowed. Partially, the physics of stellar feedback are determined by the laws of electromagnetism, nuclear physics, and thermodynamics. Those laws do not become more lenient at high redshift. A supernova at redshift 12 releases the same energy as a supernova observed in the nearby universe. The radiation from a massive hot star at redshift 10 is governed by the same physics as the radiation from a massive hot star forming today in the Milky Way. The early universe was different from the present universe in some ways: higher temperatures, higher densities, different gas compositions. But the fundamental processes that limit star formation efficiency do not turn off at high redshift. They operate as they always have. This is where the star formation efficiency track approaches a physical ceiling. The early universe conditions may have allowed somewhat higher efficiencies than we observe today, lower metallicity gas cooled differently. Early stellar populations were more massive and shorter lived in ways that changed the feedback balance. These are legitimate scientific questions. But the required efficiency, at least for the most extreme Webb findings, starts to press against limits set not by the model but by the underlying physics of how energy is released and distributed in stellar environments. and if neither the matter nor the efficiency can explain it, then a smaller number of scientists have begun asking a larger question. The phrase new physics does not mean what most people think it means. In popular usage, it has become shorthand for science fiction, for exotic phenomena that have no connection to tested reality, for theories that exist outside what anyone could ever confirm or refute. That framing is not what the term means in physics. New physics, in the technical sense, refers to a modification to a known physical framework that changes its predictions in specific, testable ways. It is an extension of the known into territory where the old framework's predictions no longer match observation. It is precisely what general relativity was to Newtonian mechanics, and what quantum mechanics was to classical physics. The history of physics is, in large part, the history of new physics. Quantum mechanics was new physics relative to classical mechanics. It required accepting that particles could exist in superpositions of states, that measurement itself affects outcomes, that the determinism of classical physics breaks down at the atomic scale. General relativity was new physics relative to Newton. It required accepting that space and time are not fixed backgrounds, but dynamic entities that curve in response to mass and energy. The standard model of particle physics introduced new physics relative to everything that came before it. It unified the electromagnetic force with the weak nuclear force, predicted the existence of the Higgs boson decades before it was detected, and established the mathematical language that describes matter and energy at the most fundamental scale currently accessible. Each of these frameworks was not a rejection of prior knowledge, but an extension of it, one that made new predictions that could be tested, and that in every case eventually were. The third response track to the Webb findings begins with physicists examining whether the standard cosmological model's treatment of certain phenomena might require exactly this type of extension. One area under renewed examination is the behavior of gravity on galaxy scales. A framework called MOND, Modified Newtonian Dynamics, was proposed in 1983 by physicist Mordechai Milgrom at the Weizmann Institute in Israel. MOND suggests that gravity does not behave exactly as Newton's equations predicted extremely low accelerations, the regime that governs the outer regions of galaxies, far from their centres, where the gravitational force is weak. In that regime, MOND proposes gravity falls off more slowly than Newton predicts, producing the flat rotation curves observed in galaxies without requiring dark matter. MOND has been developed and extended since Milgrom's original paper by a number of researchers. Stacy McGough at Case Western Reserve University has been among its most rigorous advocates, publishing detailed comparisons between MOND predictions and galaxy rotation data across a large sample of galaxies. Pavel Krupa at the University of Bonn has argued that the failures of direct dark matter detection, combined with the accumulating cosmological anomalies, deserve a serious reconsideration of the dark matter paradigm. Neither is arguing for abandoning rigor. Both are arguing that the data is pointing somewhere. A second area under examination is the inflationary epoch, the brief period, in the first tiny fractions of a second after the Big Bang, during which the universe expanded at a rate that dwarfs anything in the universe's later history. The details of inflation, exactly how it began, how it ended, what its energy scale was, how long it lasted, are not directly observable. The cosmic microwave background, our earliest observational window, comes from a period 380,000 years after the Big Bang, long after inflation had ended. The initial conditions of structure formation, the tiny density fluctuations that seeded all later structure, were imprinted by inflation. If inflation proceeded differently from what the simplest models assume, the initial seeds for structure formation might have been different in amplitude or in their distribution across scales, potentially allowing structure to grow faster in the early universe than the standard model predicts. A third area involves a proposal called early dark energy, a modification to the standard cosmological model in which a form of dark energy, distinct from the cosmological constant that drives the current accelerating expansion, existed in the early universe and then decayed away. Early dark energy would have affected the expansion rate during the period when the first structures were forming. Some versions of this proposal were already under discussion because of the Hubble tension, and the Webb findings have given the idea additional reason for investigation. The difficulty is that early dark energy proposals struggle to explain all the relevant observational constraints simultaneously. Each of these proposals makes specific predictions. Each of them can, in principle, be tested against future Webb observations, future large-scale surveys of galaxy populations, and more precise measurements of the cosmic microwave background power spectrum. That testability is what makes them science rather than speculation. But each of them also creates new problems it must explain. MOND has profound difficulty accounting for the large-scale structure of the universe at scales where dark matter's effects have been precisely confirmed. Modified inflation scenarios must not disturb the careful agreement between lambda CDM and the existing CMB measurements. Early dark energy proposals face the challenge of the Hubble tension being more complex than any single modification has yet fully resolved. None of these three response tracks has closed the gap. What Webb opened in the summer of 2022 remains open. What makes the Webb findings genuinely difficult to resolve is not any single layer of the problem. Each layer, considered in isolation, might be manageable. The time problem alone, the fact that the observed galaxies are too massive for the time available, could, with some assumptions, be addressed by modifying how efficiently the early universe formed stars, or by adjusting dark matter behavior to accelerate structure formation. The metallicity problem alone, the presence of heavy elements that require prior stellar generations, is challenging, but might conceivably be addressed by invoking highly efficient early star formation cycles that ran through their timelines quickly. The abundance problem alone, the sheer number of massive early galaxies across multiple surveys, is statistically difficult to dismiss, but might point to a single parameter in the model that is set incorrectly. The difficulty is that these layers are not independent, they are connected, and the connections form a structure that is much harder to address than any single component. In 2023, astronomer Michael Boylan-Colchin at the University of Texas at Austin published a paper in Nature Astronomy titled Stress Testing CDM with High Redshift Galaxy Candidates. The paper did not argue that lambda CDM was wrong or that it should be abandoned. It examined how far the model could be stretched while still remaining internally consistent, and it identified specific constraints that the Webb findings, if confirmed at their current values, would place on any modification to the standard framework. The paper was careful, methodical, and grounded in the model's own mathematics. Its conclusion was that the most extreme Webb findings, if taken at face value, place lambda CDM under stress that goes beyond what parameter adjustments can relieve. The core of the problem Boylan-Colchin identified is what can be called a constraint structure. Every attempt to accelerate galaxy formation in the early universe, whether by modifying dark matter, increasing star formation efficiency, or adjusting the initial conditions from inflation, must operate within limits set by other confirmed observations, and those limits interact with each other in ways that prevent any single modification from solving all of the problems simultaneously. Consider the constraint in concrete terms. Increasing star formation efficiency to explain the observed stellar masses requires the early universe to convert gas into stars at a rate far above what feedback physics currently allows. But the same feedback processes, supernova winds, radiation pressure, black hole jets, that limit star formation efficiency also regulate how quickly galaxies chemically enrich their gas. If you suppress feedback to allow higher efficiency, you also change the chemical enrichment timescale. A galaxy that converts gas to stars at high efficiency does so in a way that also changes how and when heavy elements are distributed through that galaxy's gas reservoir. The metallicity problem and the time problem are not separate constraints on separate aspects of galaxy formation. They share the same underlying physical processes. The metallicity problem and the time problem are not separate constraints on separate aspects of galaxy formation. They share the same underlying physical processes. This is what makes the problem structurally different from a situation where multiple independent anomalies happen to appear in the same telescope's data. If the time problem and the metallicity problem were caused by different, unrelated aspects of galaxy formation, if you could fix the timing by changing one parameter and fix the metallicity by changing a different parameter without those changes interacting, then the path to a solution would be clearer. You would have two levers and you would pull both. But they are not independent. The stellar feedback processes that determine how quickly a galaxy can accumulate stellar mass are the same processes that determine how quickly it can chemically enrich its gas. You cannot independently tune the mass accumulation rate and the chemical enrichment rate. They are governed by the same underlying physics, the same stars, the same explosions, the same radiation fields. This is the structural nature of the constraint. It is not that the model faces many problems, it is that the problems are interlocking, and the mechanism by which you might solve one tightens the constraints on the others. Similarly, modifying dark matter to provide larger halos earlier, to give galaxies more gravitational scaffolding in the early universe, changes the abundance and distribution of those halos across a range of mass scales. But the abundance of dark matter halos at different mass scales is itself a well-tested prediction of lambda CDM. It has been confirmed by galaxy cluster counts at various redshifts, by weak gravitational lensing surveys that measure the mass distribution of the universe statistically, and by the statistics of galaxy clustering at intermediate redshifts. Changing the halo mass function to fix the early galaxy problem at high redshift risks, breaking the agreement between lambda CDM and those lower redshift observations. A model that fixes redshift 10 but breaks redshift 2 is not a solution, it is a different set of problems. Boylan-Kolchin's paper was not a polemic. It was a technical analysis published in one of the most respected journals in the field, by a researcher working within the mainstream of cosmology. The conclusion was measured, the Webb data, if the most extreme redshift and mass measurements are confirmed, places lambda CDM under stress that cannot be relieved by minor parameter adjustments. The field is not facing a puzzle, it is facing a structural challenge. The map we drew of the early universe and the universe that Webb is showing us are, in meaningful ways, two different places. Science does not stop at a crisis. The same instrument that produced the problem is producing the data needed to resolve it. Webb is not a telescope that took a few controversial images and went dark. It is an active observatory with a designed operational lifetime of at least 10 years, a scientific mission queue extending years into the future, and a community of astronomers around the world who are, at this moment, using it with specific intent to either confirm or constrain the anomalies that have emerged. Several major survey programs are currently addressing the early galaxy problem directly. Cosmos Webb is a large program covering roughly half a square degree of sky, a significant area by Webb standards, with the specific goal of mapping galaxy populations at high redshift across a wide enough field to produce statistically reliable samples rather than single-field snapshots. Wide area coverage matters because rare, extreme objects are more likely to show cosmos. Webb is also designed to detect galaxies across a range of redshifts, not only the most extreme ones, so that the full population of early universe galaxies can be mapped statistically, not only the outliers that catch immediate attention, but the distribution of all galaxies at high redshift against which the lambda CDM. Predictions can be directly compared. JADES, the JUST Advanced Deep Extragalactic Survey, is doing something different. Rather than covering a wide area with moderate sensitivity, JADES is going extremely deep in a smaller field, pushing Webb to the limits of its sensitivity to detect the faintest and most distant objects accessible to the telescope. JADES has already produced some of the most extreme high redshift conformations in Webb's early operational period, including galaxies at redshifts approaching 15, corresponding to the universe at less than 300 million years old within the first 2% of cosmic time. PRIMA, the public release imaging for extragalactic research, covers two well-studied fields where extensive archival data from Hubble. SPITZER and other observatories allows direct comparison between what was seen before Webb and what Webb adds. This comparative approach helps distinguish genuine physical anomalies from artifacts of a single instrument's calibration or observing strategy. When Webb finds something that Hubble could not see in the same field, and the two datasets are consistent with each other in the objects they do share, confidence in the new detections increases considerably. Ground-based observatories are contributing independent confirmation. The Very Large Telescope in Chile and the Keck Observatory on Mauna Kea in Hawaii are conducting spectroscopic follow-up on photometric candidates identified by Webb, converting colour-based redshift estimates into precise, confirmed measurements using instruments entirely separate from Webb's systems. Every spectroscopic confirmation from a ground-based telescope is an independent validation that does not rely on Webb's photometric calibration. Looking further ahead, the Nancy Grace Roman Space Telescope, currently scheduled for launch in the mid-2020s, will cover sky area many times larger than Webb can practically survey in its operational lifetime, at infrared wavelengths similar to Webb's, and with a sensitivity designed specifically for wide-field galaxy population studies. Roman will provide the large number statistics that Webb's relatively narrow survey fields can only begin to establish. The Vera C. Rubin Observatory in Chile, conducting a 10-year survey of the southern sky, will provide complementary wide-area photometric data and enable statistical analysis of galaxy populations at a scale that no prior survey has achieved. What is being assembled across all of these programs is not a verdict, it is a dataset. A dataset that within the next 5 to 10 years should be large enough, well confirmed enough, and independently cross-checked enough to determine whether the early galaxy problem is a persistent feature of the universe or an artifact of the early phase of Webb's operations. If the anomalies persist in larger samples with higher spectroscopic confirmation rates, if the overabundance factor remains at 10 to 100 times the model's predictions across statistically robust wide-area surveys, then the field will have to confront the constraint structure that Boylan Kolchin and others have described, with the full weight of the data behind it. Every image Webb returns adds to a picture that is, at this moment, still being assembled. A cosmological model is not a single claim. Lambda CDM is not one equation. It is a system, a set of interconnected descriptions covering how matter behaves on large scales, how the universe expands, how structure forms and evolves across cosmic time, how the first light propagated through the early universe and left its imprint on the cosmic microwave background, how the lightest elements were forged in the Big Bang's first few minutes, and how the heavier ones were built up over billions of years in stellar cores. The components of this model are connected to each other in specific mathematical ways. A change to one part of the system changes what other parts predict. This matters because the early galaxy problem does not live in isolation within lambda CDM. It lives in the part of the model that describes early structure formation, how the first overdensities in the young universe grew into the first halos, the first proto-galaxies, the first structures visible to a telescope. An early structure formation is connected through the model's mathematics to several other phenomena that have been independently tested against observation. One of those connections is to reionization. After the first few 100,000 years, when the cosmic microwave background was released and the universe became transparent to light for the first time, it quickly filled with neutral hydrogen, atoms that had formed when the universe cooled enough for electrons to bind to protons. That neutral hydrogen was opaque to ultraviolet light. As the first stars and galaxies ignited, they began producing ultraviolet radiation that gradually ionized the surrounding hydrogen, converting the universe from an opaque neutral state to the transparent ionized state we observe today. This process is thought to have proceeded from roughly 400 million to 1 billion years after the Big Bang. Its timing and character are constrained by observations of distant quasars, which show signatures of neutral hydrogen absorption at specific redshifts, and allow astronomers to trace how the ionization front progressed through the early universe. If the early galaxy population was more abundant and more luminous than lambda CDM assumes, the sources of ionizing radiation were more numerous and appeared earlier. Reionization may have proceeded differently from what the standard model predicts. The quasar observations that currently constrain reionization's timing would then need to be reinterpreted within a revised framework. A second connection runs to the cosmic microwave background itself. The CMB power spectrum, the precise pattern of temperature fluctuations across the sky, measured with extraordinary precision by the Planck satellite, is one of the most powerful tests of lambda CDM in existence. The model fits the CMB data to within fractions of a percent across a wide range of angular scales, but the CMB was laid down at a specific epoch, and the model parameters that produce the best fit to the CMB also produce specific predictions for how structure grew from that point forward. If the early universe formed structure differently than the model assumes, the connection between the CMB era physics and the later structure that grew from it requires re-examination. The CMB fit may or may not survive that re-examination, depending on what the Webb findings ultimately require. A third connection is to inflation itself. The density fluctuations that seeded all galaxy formation were imprinted during the inflationary epoch, that brief extraordinary period in the first fractions of a second, when the universe expanded at a rate that dwarfs anything in its subsequent history. The amplitude and scale dependence of those fluctuations, as measured in the CMB, are consistent with the predictions of the simplest inflationary models. If the early galaxy observations require different initial conditions than these simplest models produce, then the question of what inflation looked like, already among the most open questions in fundamental physics, becomes both more pressing and newly constrained by the galaxies Webb is finding. What we genuinely do not know is whether the anomalies Webb has found are pointing toward a modification within the lambda CDM framework, a change to dark matter behavior or star formation physics that leaves the model's foundations intact, or whether they are pointing towards something in the foundations themselves. The honest answer at this stage of the data is that the science has not finished. Every scientific revolution begins the same way, not with a wrong answer, but with a question that the previous answer could not contain. Here is what we know, and what we do not. We know that Webb has detected galaxies at redshifts above 10 with spectroscopic confirmation, objects that existed when the universe was less than 500 million years old, seen as they were in the first 3 to 4% of cosmic time. We know that several of these galaxies have estimated stellar masses that exceed what lambda CDM's hierarchical assembly process can produce in the available time. We know that at least some of these galaxies show spectroscopic signatures of chemical elements that require prior stellar generations, adding a second independent time constraint on top of the mass constraint. We know that the number of massive early galaxies detected across multiple independent surveys exceeds the model's predictions by a factor of 10 to 100. We know that 3 response tracks have been proposed: modifications to dark matter, revisions to star formation efficiency, and extensions to the physical framework itself, and that none of them, individually or in combination, has yet closed the full gap between prediction and observation. We know that the constraint structure identified by Boylan, Colchin and others means that fixing one layer of the problem tends to create pressure on another, preventing a simple parameter adjustment from serving as a resolution. We do not know whether the overabundance of massive early galaxies represents a parameter error, a model error, or a physics error. We do not know what the 3 response tracks will produce when tested against the larger datasets that Roman and Rubin will eventually provide. We do not know whether the Hubble tension and the early galaxy problem share a common root or represent 2 separate cracks in the same foundation. We do not know, because the data is still being collected and analysed. We do not know, because the data is still being collected and analysed. We do not know, because the spectroscopic confirmation rate for the most extreme candidates is still growing. We do not know, because the wide area surveys that would establish the statistical robustness of the abundance anomaly are still in progress. Science in the middle of a discovery looks exactly like this: a set of results that do not fit the best available model, a community of researchers working with intent and rigour to determine what the results mean, and a process that has not finished. This is not a failure. It is a procedure. This is not a failure. It is a procedure. The procedure is not comfortable to be inside. Scientists who have spent careers building lambda CDM, refining its parameters, testing its predictions, using it as the foundation for everything they do, they are not celebrating this moment. They are doing what scientists do, looking harder at the data, running more simulations, proposing modifications, designing new tests. The emotional experience of a scientific crisis is not the exhilaration that the word discovery sometimes implies. It is closer to the experience of a navigator who has been sailing confidently using a chart, and who has realised that the coastline does not match. The chart is not useless, it got the ship this far, but the navigator now has to reconcile the chart with what the instruments are showing, and that reconciliation is careful, slow, and not yet finished. Every model in the history of science that eventually broke did so because someone built an instrument precise enough to see what the model could not accommodate. Ptolemy's model, held until telescopes, showed moons orbiting Jupiter in paths that did not centre on Earth. Newton's mechanics, held until measurements precise enough to detect Mercury's perihelion shift, demanded an explanation Newton's equations could not provide. The steady-state universe, held until an antenna sensitive enough to detect the cosmic microwave background, registered the afterglow of the Big Bang. In each case, the instrument that found the discrepancy was built not to break a model, but to observe with greater precision than had been possible before. The breakage was a consequence of the precision, not the intent. Webb was not built to find something wrong. That was never the plan. The plan was to see the early universe with greater clarity than any instrument before it, and to use what it saw to confirm and deepen our understanding of how the cosmos came to be. The telescope worked exactly as designed, and in working exactly as designed, it returned images of a universe that our best model of reality did not predict. Not in a small way, not in a way that a calibration adjustment can absorb. In a way that the field has, in its own careful language, called a crisis. There is something in this that carries weight if you sit with it long enough. Every time a model has broken in this way, every time an instrument has shown us something that the reigning framework could not contain, what followed was not the collapse of understanding. What followed was the discovery that the universe was larger, more intricate, and more precisely ordered than the model had been able to see. Copernicus did not impoverish the night sky. He revealed it to be something more than it had appeared. Einstein did not make Newton wrong. He showed that Newton had been describing a corner of a larger truth. Whatever Webb is pointing toward, a modified parameter, a revised assumption, a new physical principle at the edge of what the inflationary epoch left written into the fabric of the universe. It is pointing towards something, not toward nothing, not toward disorder, toward a more complete description of a cosmos that has been here for 13.8 billion years, assembling structure in the dark long before any mirror existed to catch its light. The telescope was not built to find something wrong, but it found something, and what it found is still unfolding. Good night.